Okay, let's go ahead and get started. Homework, quizzes, and exam corrections are being passed around, so make sure that you get those out, whatever's left in the classroom at the end of the day. I'm not taking home with me again, so if you want it, take it. If there's a friend who's not here, take it for them. So today we're moving on to a new chapter. I don't know why. We're not moving on to a new chapter. We're continuing on with chapter 11 and finishing off chapter 11. There's a slight change in the schedule. Today's lecture was just supposed to be second law analysis, but it sort of seemed to me that I couldn't spend a whole lecture on the second law analysis for heat pumps, refrigerators. So I've combined that with the next innovative refrigeration systems lecture. So those two are combined into one. And as a consequence, I'm going to break up lecture 16 into 2 days. So when we talk about the thermodynamic property relations and we actually go into some of the math and the partial derivatives and a little bit of calculus, that will be covered over 2 days rather than just 1 day. So I think it'll give you a better chance of understanding the fundamental math that is involved. And it'll reduce the amount of time that we spend on something that I could make up a full lecture on, but probably I don't need to make up a full lecture on it because we do second law analysis now for each piece and each component of what we're learning. So it's not really the theory and the fundamentals are not changing, it's just doing more problems using the same equations. So we'll talk about it today, but the next lecture is going to be on thermodynamic property relations, and that'll be over 2 days, so Thursday and the next Tuesday we'll do it. And then if you are looking at your schedule, there's an exam on October 26th, so that's coming up in a couple of weeks, just to put that out there. So you should be hopefully studying already. If there's difficulties that you're having on the homework, you're not understanding how to approach these cycles, you can't find the right property values, get those keys worked out before we get to the day before the exam. So visit me in office hours, send me an email, whatever you need to do so that we can work that out. So today, as I mentioned, we're in chapter 11. We're finishing chapter 11. My computer's running all sorts of weird things. I don't know why, because I restarted it. So when we were looking at the ideal vapor compression cycle, from state 1 to 2 is isentropic compression, state 2 to 3 is isobaric heat rejection, state 3 to 4 is isenthalpic. What does that word mean? Okay, constant enthalpy, isenthalpic. And then 4 to 1 is isobaric heat absorption. So this is the ideal vapor compression cycle that we've been looking at for chapter 11. It's just a very basic simple cycle consisting of 4 steady state, steady flow engineering devices. So it's used for refrigerators, it's used for air conditioners, and it's also used for heat pumps because we just can change which side of the vapor compression cycle we're looking at. So for a heat pump, we're trying to add more heat to a warm environment, whereas with refrigerating, we're removing heat from a cold environment to try to make it colder. And we looked at the ideal vapor compression cycle, where the area under the curve is representative of the heat transfer, and we looked at how we could potentially improve the coefficient of performance by increasing T sub H or lowering T sub L. So for a heat pump or for a refrigerator, the coefficient of performance we can determine just based on the desired outcome, so whether it be removing heat or adding heat, and then using property values we can calculate Q sub L or Q sub H. And then this work net in, of course, for this ideal vapor compression cycle with a throttling device rather than a turbine is easy to calculate. It's just H2 minus H1. If we add a turbine in, then we have to subtract off the amount of work that the turbine would contribute because it reduces our overall network input. Then we talked about the actual vapor compression cycle where there's irreversibilities present that we can't completely ignore, although we did choose to ignore some, like pressure drops in the condenser and things like that. But these irreversibilities lead us to the discussion of second law analysis, right? So we need to think about how these ideal devices are operating in a non-ideal way. And as a consequence, we lose some of this potential to contribute to energy creation, not energy creation, but energy use. That rather than using our energy in a very efficient and effective way, sometimes we waste it. Okay, so if we want to look at the exergy analysis for the ideal vapor compression cycle or the actual vapor compression cycle, then we can look at it piece by piece, similar to what we've done for other cycles. So for the compressor, the analysis is just that the exergy destroyed from state 1 to 2 is going to be the mass flow rate multiplied by this T naught. You see my mouse? Yeah. T naught, which is what? What is T naught? Temperature of the surroundings, which we also consider to be the dead state, right? Multiplied by the change in entropy. And this, of course, is assuming that this compressor doesn't have any heat transfer with the environment. So we're neglecting any heat transfer with the environment. That's not included in our exergy calculation. We can use the exergy recovered, which will be the amount of reversible work that this compressor could produce, divided by the amount of actual work which is put into this compressor to determine the second law efficiency of the compressor. And then we can also determine that second law efficiency using property values, or if we were to look at it in terms of the flow exergy, we can also compute it that way. For the condenser, the analysis is similar. The main difference is now we have this heat transfer component that we have to account for in our exergy destruction. So anytime we transfer heat across a temperature interval, we destroy exergy. So it certainly contributes. We're losing heat. Heat is removed from the system, so our exergy, there is additional exergy being destroyed. The exergy recovered is the potential exergy of this Q that is leaving the system, and then the exergy expended is the exergy change from 2 to 3. So again, we can calculate the exergy destruction, we can calculate the second law efficiency of the condenser. Similar analysis for the expansion valve, but in this case, because an expansion valve doesn't have any heat transfer and it doesn't do any work, there is absolutely no exergy recovered in the process. So the second law efficiency for an expansion valve is 0, meaning that there's no way of recovering that work in a reversible or an irreversible way. And you can look at it another way, that if we look at it in terms of the property values, it's 1 minus this exergy destroyed from 3 to 4 divided by the exergy change, which just ends up being 1 minus 1, which is 0. And then for the evaporator, similar to the condenser, we now have heat exchange with the environment, but in this case we have a heat input which serves to decrease the exergy destruction. Because we have heat coming into our system, we're gaining the potential to do work in the amount of this x dot term. And similar to all the others, we can calculate our second law efficiency as well. So for a reversible system, this x dot QL is going to be equal to this Q sub L dot times T naught minus TL over TL, which is equal to the reversible work in. We'll need that a little bit later in our example. So if we're looking at it as a heat pump, we're going to assume that T sub L is equal to our dead state, and that our evaporator second law efficiency will be 0 for a heat pump. So if we want to find the total cycle exergy, we just add those 4 terms together. The total exergy destroyed is going to be equal to this net work input minus this heat Q sub L that's entering the system. So we can also calculate the second law efficiency of the cycle, and if our work in is equal to Q sub L over the coefficient of performance, then we can rewrite this efficiency, or the second law efficiency, in terms of the coefficient of performance and the temperatures within the system. So you can see here that the T sub L, or T naught minus T sub L, If we're looking at our dead state is T sub L, then that would blow up. But in this case, our warm environment is actually going to be the environment of the surroundings. We can also calculate this second law efficiency just using the coefficient of performance for a reversible cycle and for the actual cycle. And similarly, if this were operating as a heat pump rather than a refrigerator, we could use the coefficient of performance for the heat pump instead, which is just a slightly different equation because the heat pump has Q dot H instead of Q dot L in every place that the refrigerator has Q dot L. Okay, so lots of equations. I'm sure you're not exactly specifically following each equation. Let's do an example with second law analysis of a vapor compression refrigeration cycle. In your homework, I think I asked you actually to do vapor compression heat pump. So make sure that as you're going through this, you understand the difference between a heat pump and a refrigerator and how you would change the analysis to do it as a heat pump rather than a refrigerator. Okay, so in this case, we have a refrigeration cycle with R134A as the working fluid, and we're using it to maintain a space at negative 13 Celsius by rejecting heat to the ambient air at 27 Celsius. So right here, as we're given these temperatures, this 13 Celsius and this 27 Celsius, where do they fall into place on this diagram and what do they mean physically?
Negative 13 is the cold refrigerated space.
Okay, so this negative 13 degrees Celsius is here. It's T sub L, right?
And 27 degrees Celsius is the T sub H.
Is T sub H. And which one of those is going to be our dead state?
T sub H.
T sub H, right? Because that's just the environment that we're surrounded by. So in this case, our system or whatever we're analyzing, this refrigerator, is going to have a temperature that's colder than the dead state, which means in order to come into thermal equilibrium with the dead state, heat needs to be added to it. Okay, if we were to think about that. Okay. R134A enters the compressor at 100 kilopascals, and it's superheated by 6.4 degrees Celsius. What does that mean?
It's 6.4 degrees Celsius hotter than the superheated state at 100 kPa, or the saturated state at 100 kPa.
Okay, so this 6.4 degrees Celsius, this means it's Tsat at 100 kilopascals plus 6.4 degrees Celsius is going to be equal to the temperature at state 1. Okay, now notice this 6.4 degrees Celsius. Should I convert 6.4 degrees Celsius to Kelvin?
When
No.
looking up,
Why? Okay, it's a delta T. It's a difference in temperature between this state and the environment. So how do I convert a difference in temperature in Celsius to Kelvin?
1 to 1.
It's 1 to 1, it's the same. So 6.4 degrees Celsius is the same as 6.4 Kelvin because it's a delta T. It's a temperature that's higher than another temperature. If you were to convert 6.4 to Kelvin and then add it to your Tsat, you would get a wildly wrong answer. It'd be significantly hotter than it was meant to be. Okay, the isentropic efficiency of the compressor is 85%, and the refrigerant leaves the condenser at 39.4 degrees Celsius as a saturated liquid. So what state is that? Leaving the condenser.
3.
State 3. So 39.4 degrees Celsius as a saturated liquid. X is equal to 1 or 0?
0.
0. Okay, so we're superheated at state 1. We're a saturated liquid at state 3, pardon me. States 2 and 4, we'll have to determine what those are. Okay, so we want to find the rate of cooling provided. What term is that? What is the rate of cooling?
Q sub L.
Q sub L, or the rate of cooling.
Q dot.
Q dot sub L is the rate of cooling. If this problem said instead the rate of heating, what value would I be looking for? Q dot H. Okay, the coefficient of performance of the system for the refrigerator, the exergy destruction of each component, and the minimum power input. Okay, so this minimum power input, that was that little addendum on one of the slides previously. So let's get started on this example. I have a big one, takes 2 pages. Because we're calculating a lot of different things, but it's not difficult. We just have to be careful with our numbers. So we start off defining the states. State 1 is fully defined, it's 100 kilopascals, and the temperature is equal to Tsat plus 6.4 degrees Celsius, which ends up being 20 degrees Celsius, because Tsat, or negative 20, sorry. Tsat is negative 26.4 degrees Celsius. So we find at state 1, we can look up our enthalpy value is 239.52 kilojoules per kilogram. And S1, our entropy, is 0.9721 kilojoules per kilogram Kelvin.
So do you find those based off the pressure, the temperature you found?
Temperature and pressure, because it's superheated. Superheated by 6.4 degrees Celsius. So if we're looking at a picture of the dome, if it were right here, that was supposed to be on the line, sorry. Right here, still not drawing on the line. Imagine that dot is on the line. Then we would be exactly a saturated vapor. But instead, we're 6.4 degrees Celsius higher than that line. So where does that put us?
Just in no man's land up above it?
It's not no man's land. We're superheated. Superheated. Okay, so we're taking our liquid that's a saturated vapor, and if it's 6.4 degrees C higher than it was when it was a saturated liquid, it'll be a superheated vapor. And in the superheated vapor region, we need to know 2 independent properties. So in this case, the pressure and the temperature of negative 20 degrees Celsius.
So it's superheated at freezing temperatures?
It's not freezing for the refrigerant.
Oh, yeah.
It's not water.
Okay.
R134A. Okay, so state 1, we have defined state 2. We know that the pressure at state 2 is what? Or do we know any information about it?
Ideally, the entropies are equal.
Okay, ideally, state 2S, S2 is going to be equal to S1. But what's our other property value? How do we figure out state 2?
I mean, you know the isotropic efficiency.
Okay. So, but in order to use the isentropic efficiency of the compressor, it's equal to H2S minus H1 over H2 actual minus H1. And right now, H2S and H2 actual are unknowns.
Can we work backwards from the condenser to state 3?
Yeah, so we need to work backwards from here. Right now, we're given a temperature in the condenser and that it's a saturated liquid. We are going to assume that our pressure is constant through the condenser. So we can use this to figure out the pressure of the condenser and then use that as our second value. So this 39.4 degrees Celsius seems like a weird number, but the reason it's that is because Psat at 39.4 degrees Celsius is 1,000 kilopascals. So we can find that our pressure here is also 1,000 kilopascals. We're neglecting any pressure drops through the condenser because we're not given any other information that would allow us to solve this problem. Okay, so if our pressure is 1,000 kilopascals and our entropy is the same as state 1, we find that H2S, so the isentropic enthalpy, would be equal to 289.14 by interpolation in the table, kilojoules per kilogram. But we don't want H2S. What do we want?
H2 actual,
We want H2 actual, and how do we find that?
using the isentropic.
Using the isentropic efficiency in this equation. So H2 actual is going to be equal to H2S minus H1 over the compressor efficiency plus H1.
How do we know it's 1,000?
Okay, so if you look in your book on table A12, or maybe A11. Actually,
It's 12.
so if we look for where this saturation temperature is 39.4 degrees Celsius, it's actually 39.37, but it's 1,000 kilopascals. So we find the pressure at state 3, yes?
When you assumed the pressure was constant in the condenser, is that just because it's ideal, or should?
Well, this is not an ideal cycle,
Okay.
but we're not given any other information to solve this problem.
So, like in the future, should we still make that assumption?
Yeah, in the future, we can usually neglect any pressure drops in the condenser and the evaporator. Primarily, pressure drops are larger in the piping and components before you get to the condenser and the evaporator, because you're going through phase change and it's easier to maintain constant pressure through there. Yeah, so that is an assumption that's a fair one to make, even if it's not an ideal system, is that you neglect any pressure changes in the condenser or the evaporator. And particularly if you're not given a different pressure over here, there's no way to solve this problem, because you have to have those two independent variables. Yes?
So you interpolated at 39.4 degrees Celsius?
I didn't have to interpolate, I just went to table A12, and it's 39.37 is the saturation temperature. So they just rounded, I rounded 39.4 to 39.37 to get 1,000 kilopascals. You could round, interpolate and find exactly what it's going to be, but it's going to be like 999 point something something something. And if you do that, then anytime you look up anything at 999 point something something something, then you have to interpolate in the other tables.
Why were you on H1 and A11?
So on A11, I could do the same thing where I could interpolate and I could find the pressure. But on A12, it's easy to see that 39.4 is 1,000 kilopascals.
So either way, it's just easier.
It's just easier because I just looked at it. You could use either table. But again, if you interpolate and you find something that's 999.98, I give you permission to just look it up at 1,000 kilopascals in the table instead of interpolating every single time. It's close enough. We're making assumptions on everything anyway. That 0.1% difference is not going to affect our final answer. Okay. Any other questions on this as we're moving through? So we've fixed state 1. We're fixing the isentropic state 2. We found the actual enthalpy is going to be equal to 297.90 kilojoules per kilogram. And this is a good moment to do a reality check that our actual enthalpy should be higher. And then we use this actual enthalpy to find our actual entropy, because we need that later when we're calculating the exergy. And we see that that is 0.9984 kilojoules per kilogram Kelvin. We had to interpolate that value. Okay, and again, we do a reality check. Our actual entropy is higher than our idealized situation, right? Because in the real case, our entropy will always increase. It won't stay the same. Okay, state 3 is easy to look everything up. We just use the saturated liquid values. So H3 is 107.34 kilojoules per kilogram. And S3 is 0.39196 kilojoules per kilogram Kelvin. And then state 4, how do we find the values there? What's our pressure? 100 kilopascals. Okay, what's our second independent intensive property?
It's isothermal.
Isenthalpic, so H4 is equal to H3, which is the 107.34 kilojoules per kilogram. And then using these two values, we go to the table and look up our enthalpy, or entropy, S4, 0.4368 kilojoules per kilogram Kelvin by interpolation in the table. Okay, so we now have the enthalpy and the entropy at all of the states. We can calculate everything that we need. So let's go to the next slide, give us a little bit of room. Oh, I didn't put in a blank. Oops, I have one. That's easier. Okay, so the first question is the rate of cooling provided. Part B is the COP, part C is the exergy destruction, and D is the minimum power input. So for part A, the rate of cooling provided, what term is that again?
Q dot L.
Q dot L. So Q dot L is equal to M dot times H1 minus H4. So the rate of cooling is what happens across the evaporator. So H1 minus H4. So M.dot's given to us in this problem of 0.05 kilograms per second. H4 is 239.52. Oh no, H1 is 239.52. H4 is 107.34 kilojoules per kilogram. So we find Q dot L is equal to 6.609 kilowatts. Okay, part B, we're supposed to find the coefficient of performance for a refrigerator. What is the equation for that?
Over work done, or work in.
Okay, so Q dot L, which is our desired outcome, over the work dot in, and in this case there's no work out, so it's just the compressor work. So we can use this 6.609 kilowatts divided by our work in, which is going to be M dot times H2 minus H1. So M dot again is 0.05 kilograms per second. We can look up H2, H1. We have those values. We find that our coefficient of performance is 2.264. And there's no units on that. Unless okay, part C is the exergy destruction at each state. I'm going to skip that for now just because it takes up so much room to write all that. And I'll go to part D, which is our work dot minimum. So this minimum work for the compressor is going to be the case where our compressor is reversible. We know that the coefficient of performance for a reversible refrigerator is equal to T sub L over TH minus TL. That's from the Carnot cycle. So we can calculate that as T sub L is 260 Kelvin, T sub H is 300 Kelvin, minus 260 Kelvin. So we find the reversible COP is equal to 6.5. So we can also say that our COP reversible is equal to this Q dot L over our work dot min reversible. Or in other words, our minimum work is equal to Q dot L over our reversible COP. So we find this is equal to 6.609, which is our QL that we saw before, divided by our reversible COP, which is 6.5. So we find that our reversible work is equal to 1.017 kilowatts. So that's the minimum amount of work that we could put into this system if it were a reversible system. And our actual compressor power is higher. Okay, so we've done the easy ones. Let's go to part C. It's not that this is difficult, you just have to write a lot more. So exergy destruction dot is equal to m dot times T0 times S out minus S in plus Q out over temperature of the boundary in minus Q in over temperature of, Q out over out, Q in over T in. Okay, so it's out minus in. So let's look at the exergy destruction from 1 to 2, which is our compressor. What terms do we need to worry about in the compressor? Do we have any heat transfer? Yeah, we're not given any information about heat transfer. We have to assume that it's adiabatic. So we have m dot T0 times S out of the compressor, which is S2, minus S1. So we plug in the numbers for that. We find the exergy destroyed from 1 to 2 is equal to 0.3945 kilowatts. So the exergy destroyed from 2 to 3, this is now the condenser. What terms do we have in the condenser? Do we have flow in, entropy coming in? The condenser?
Would 1 and 2 not just be 0, or
E0,
like the X destroyed, like, since the entropy is
for the isentropic case it would be, but we're looking at the actual case. So that's a good point, that this would be equal to 0 for the reversible case. Because our isentropic efficiency would be such that S2 would equal S1, 100% efficient, then it would be 0 for the reversible case. But it's not reversible, we found an actual entropy value. Okay, so state 2 to 3, we have entropy coming into the system with flow, we have entropy leaving the system with flow. Do we have any heat transfer in the condenser? What does a condenser do?
QH out.
Okay, we have Q leaving, right? Because a condenser takes a vapor and turns it into a liquid. How does it do that? It removes heat. Right? I see some quizzical looks. That's what a condenser does, guys. Da-da-da! What does an evaporator do?
Heats it up.
Heats it up. How's it do that? You add heat. Takes it from a liquid to a vapor. Okay. They are one and the same but opposite. So when we get to the evaporator, you guys already should know this answer. Okay, so the mass flow rate times T0 times entropy out, S3 minus S2, and for our condenser, is heat leaving or entering?
Leaving.
Heat is leaving, so it's a Q out over the temperature of the boundary out. So the exergy destroyed from state 2 to 3, we put in all the numbers, we get 0.4314 kilowatts. Exergy destroyed from 3 to 4, this is our throttling device. Do we have any heat transfer in our throttling device? Not that we know of. So we just have m dot T0 times entropy out minus entropy in. S4 minus S3. And we find this one to be equal to 0.6726 kilowatts. Why is its value so much higher than the other ones? can't get it back, right? There's no heat transfer, there's no work done, it's like you've expended all that energy. That's not to say that throttling devices aren't very useful, because they are. You can have a pressure drop without any mechanical components to do it. But they are exergy destruction devices, and that's okay. So then the exergy destroyed from state 4 to 1. This one is the evaporator. What's going on in the evaporator? You have a Q in, m dot T0 times S1 minus S4, so the entropy out minus entropy in, minus a Q in, Q dot L over T sub L. In this case, T naught and T sub L are the same value, because we're not told otherwise. So 0.4037 kilowatts for our evaporator. Okay, so we finished that example. This will be similar but different to the homework we did. Yes?
I was gonna ask, what was the difference between this and the homework?
I think in the homework it's a heat pump instead of a refrigerator,
Okay.
but that might be a different problem. Yes?
Then your X destroyed out between states 4 and 1, your M dot, like in your slides, is inside the parentheses, and it's multiplied by the quantity of S1 minus S4.
Okay, so another alternate way of writing this would be T naught times M dot S1 minus S4 minus Q dot L over T sub L. Because I already solved for Q dot L here, I don't need to do that calculation again.
Perfect.
So that's the difference there. Sorry, it takes a while to think. Do you see the difference? So here, if I multiply through M dot times S1 minus S4 and M dot times Q dot QL, then QL becomes a big Q dot L instead. And the main reason I did that was just because I already calculated it once. I didn't need to put the enthalpies in there and calculate it again. It's a little time saver. Okay. Any other questions on this example? Are you guys following it? All right. Okay, so heat pumps. And in the US, when we talk about a heat pump, the generic term heat pump, it's like saying Kleenexes. A heat pump is a refrigerator and a heat pump. Okay, because we use the same device for two purposes, to heat and to cool a home, at least here in the southern part of the US. So it operates as a refrigerator in the summertime, and you can see that the two different cycles consist of exactly the same components, but there's just a valve that switches so that it can operate running in the reverse direction so that you heat the house or cool the house. So in this case, when it's operating in the heating mode, the outdoor coil is the cold coil, the indoor coil is the warm coil. So with a heat pump in the wintertime, when it gets extremely cold, it's very often that this freezes. Okay, condensation builds up, it gets extremely cold due to humidity in the air, ice will freeze on the coils itself. So then it doesn't operate very effectively because it can't transfer heat with the environment. It's stuck at 32 degrees or whatever, and there's ice all over, so heat transfer doesn't happen very quickly. So what it does is it says, okay, now I need to go into air conditioner mode. I'm just not going to blow that air into the house. So that the outdoor coil then becomes the hot coil, and it melts all of that ice off of the heat pump so that it can reverse again and continue operation. Yes?
You said that's automatic?
Yeah, it's built in to the system.
Is that what auto defrost refrigerators do too?
Yes, similar. Yeah. So that's what's so nice about heat pumps is they're very versatile, and there are settings on the heat pump, and if you have like newer Nest thermostats or whatever, you can have it set up to just keep your house at a certain temperature, and it'll choose whether it's a heat pump or a refrigerator to accomplish that. So on days where it's 74 outside and you want your house to be 70, it might crank up the air conditioner for a little while, but then it gets it too cold and it has to switch to a heat pump or whatever. So I don't think that's necessarily the most energy efficient way to do it. But if you just like never having to touch your thermostat or adjust it, then that's an option too. Heat pumps don't work very well in environments where there are very extreme winters. Because even in West Virginia, if you have a heat pump, you more than likely have a backup, either emergency heater that is just a resistance heater. Sometimes that's coils of electric wires within the ductwork that just heat up so it can blow hot air into your house. Or you'll have like a backup furnace. Because when the temperature gets so low that the heat pump can't maintain the indoor temperature, then it has to switch to another method in order to do that. So on extreme days when we have the, what are they called, polar vortex or whatever, probably your heat pump is either running constantly or it's switching over to the backup heat, the emergency heat. And when your backup heat is resistance heaters, it's probably using like double the electricity of when, or more, of when it is working as a heat pump. So, da-da-da. All right. So now we're going to talk about some modifications to this vapor compression cycle that allow us to do more and better things. The first is the Cascade Refrigeration Cycle. So when we have a very, very wide temperature range that we want to try to overcome, let's say we're in a very hot environment and we're trying to cool something to extremely cold, sub-freezing temperatures, it's difficult to do that just in one cycle, particularly if it's some sort of an outdoor application or like ski Dubai, something like that, trying to create snow when it's 120 outside. Probably they have multiple Cascade refrigeration systems going. So rather than trying to accomplish everything in one cycle, this is similar to when we were using compressors in power generation, that we would have a two-stage compression process. So we can compress to a higher pressure in this topping cycle, and we compress to a much lower pressure in this bottoming cycle. So by separating it into two separate pressure regions, we're able to accomplish a greater temperature difference than we would if we were trying to use a single compressor to overcome that entire pressure difference on its own. So what this does is it has sort of like a regeneration process kind of in between these two cycles themselves, where if we're trying to refrigerate, then this cycle is cooling it down to a certain temperature, and then that refrigerant will exchange heat with this refrigerant in order to cool it down so that we can get to an even lower temperature. And if it were operating as a heat pump, it would be the reverse, where we would be heating up to an intermediate temperature and then heating it further to that warmer temperature. So this is a way, by stacking these two systems and operating them in this manner, that we can accomplish a much wider either pressure differential or temperature differential, depending on specifically what our application is. So we look at this on the TS diagram, you can see that maybe a single cycle would allow us to do this, or possibly if we were operating at the higher pressure ranges already, it would allow us to do this. But by stacking them both, instead of trying to go from here to here to here like this, let me change the color. Instead of trying to do this, by doing it in two separate cycles, we're able to decrease the amount of compressor work that's required from a single compressor. By using two compressors, we reduce that amount of work. So our network input is decreased significantly, which for compressors, because they use a lot of electricity, is a significant savings in cost. So adding two compressors, probably the cost of the compressor is minimal compared to the savings that you get in energy. So we can look at these similar to any other cycle where we've stacked it. In this case, it's two distinct fluids. They can be the same refrigerant or two different refrigerants, depending on which ones have the best qualities or properties at higher or lower temperatures and pressures. In many cases, it's the same refrigerant just for ease of maintenance, but sometimes it's two different refrigerants. They never mix, so it doesn't matter. But the ratio of the flow rates is going to be determined by this heat exchanger here, so H2 minus H3 over H5 minus H8. And so if we're calculating the coefficient of performance for a Cascade refrigerator, we have our Q dot L, which is here, which is H1 minus H4, and then our work net in is a combination of these two compressors. So we have to look at from state 5 to 6 and from state 1 to 2, adding the work input from those two compressors together. An alternate way of doing this is to have, instead of a heat exchanger where we exchange the heat separately, we can have a mixing chamber and a flash chamber, which allow us to mix the two fluids together through these two different compression stages, and it's a slightly different operation. In your homework, you're going to do two problems where you compare the two cycles using similar pressure differentials. So when the fluid's the same, we can just use a flash chamber instead, and what a flash chamber does is when our fluid goes through this expansion valve and the pressure drops, it's going to be a saturated liquid vapor mixture when it comes out. So if we look at actually, let's look at the property diagram for this one. State 6 here, it's a saturated liquid vapor mixture coming out of our isenthalpic throttling valve, this expansion valve here. A flash chamber allows us to drain off the liquid at state 7 and siphon off the vapor at state 3 so that we can send this vapor back through the cycle again to heat it up again. And then the liquid, we send it through the evaporator in the colder level to be compressed again. Okay, so this flash chamber, it helps us to accomplish essentially the same thing as the heat exchanger did, meaning that we're taking this higher energy fluid and continuing to put it through the cycle so that we don't condense everything and then have to heat it up again. So we're siphoning off this vapor and using it while it's still hot and just running it back through the process again. And so it accomplishes a very similar thing if we look at the diagram. So again, instead of trying to go somehow from here up like this, we're able to accomplish it using the two compressors with less overall energy input by dividing it into two stages and having this almost like a mixing chamber in there that it allows us. So this is similar, I guess, to maybe a regeneration process as well. So again, we can calculate the coefficient of performance using our values. And here, this X6, this is the quality at state 6. So the quality at state 6 will determine the mass fraction of vapor that continues on through to state 3 and then up to state 9 to combine with whatever's coming out of the first compressor. So it's kind of nice because once you know that quality value, it's easy to calculate all of the mass flow rates throughout the system. And you'll have to do this on your problem. One thing that you need to do in order to find the quality at this state is to do an energy balance there. Okay. Some additional insights on refrigeration. Sometimes we have, like in a household refrigerator, a device that has two separate compartments that are cooled to different temperatures. So we can either use two separate compressors to do that, which there are some industrial commercial refrigerator freezers that do have two separate compressors because they have a lot more space, or we can use expansion valves and make the cycle such that we don't necessarily have to have a secondary separate compressor in order to get two different temperatures. And so what they do is the gases, or the refrigerant is compressed, it goes through this condenser, it's heated up. Once it goes through the expansion valve, it's cooled to some intermediate temperature, and then it goes through a second expansion valve immediately after that and is cooled to an even cooler temperature. So this expansion valve allows this refrigerant to reduce in pressure, but by so doing it also reduces the temperature of it. So these two separate expansion valves, rather than having two separate compressors or two separate cycles for a household refrigerator, is an alternative way to accomplish the same thing that saves energy and space. So what are the disadvantages of doing that? Or can you think of any disadvantages of doing that?
Your freezer won't be as cold, right?
Yeah, that could be a disadvantage, that your freezer can't get as cold. So if you have like a separate chest freezer, those can get to much cooler temperatures than your household freezer. Another disadvantage is that there's somewhat less control over the temperature of each, and they're linked together. So if you reduce the temperature in your freezer, it automatically reduces the temperature in your refrigerator. I don't know if you've ever noticed that. You turn one down and then stuff starts freezing, or you turn one up and stuff starts defrosting in your freezer. That because they're in close proximity and they rely upon one another for this temperature differential, that it's hard to just change one without changing the other. So you kind of have to fiddle with it. And then the other disadvantage, of course, is, as you may have found, that if frost builds up in your freezer, it makes your refrigerator either hotter, depending on where the frost is building up, or colder. So you might start freezing things, or things might not be refrigerating properly if your defrost mechanism is not working properly. Okay, liquefaction of gases. So in order for gases to flow as liquids, they must be brought below this critical point temperature. Because when we're looking at gases like air, they're way up here. There's no dome visible when we're talking about air in general in these thermodynamic problems that we're working with. So sometimes we want them to be a liquid. We want them to alternate between a liquid and a gas because that allows us to get greater benefit in heat transfer. So as you go from one phase to another phase, the amount of energy that it requires to change phase is greater than just changing temperature by 1 degree. So going through phase change is important to us in these vapor compression cycles, also in power generation. So how do we do that? Well, if we want to liquefy these gases using, what do they do? Mechanical means, go away. I don't know how to make that go away. So we have, starting at state 1, we have this gas that comes in, and it's combined with gas from the previous round, and we'll talk about where that comes from in a minute. So it goes through this compressor, and right here is just demonstrated as a single compressor, but in reality it's multi-stage compression, where we're compressing and cooling, compressing and cooling, compressing and cooling, in order to get it up to this, this temperature and pressure that we want. Then we run it through a heat exchanger to remove the heat, and we go through this regenerator where it's exchanging heat with this liquid gas that's coming back in through it. So heat is being removed from this gas that we've just, that we've compressed. So we've compressed it, the heat naturally rises, we remove some heat in the heat exchanger, but it's not enough. So we remove additional heat using this regenerator, and then as we send it through this throttling valve, it turns into a liquid as we make its pressure drop rapidly. So that liquid is removed, but a lot of times it's a liquid vapor mixture, so any leftover vapor is sent back up through this recirculator in order to receive some heat from this gas that's coming through, and then it's sent back to the beginning of the process. So this makeup gas is in a much more gaseous form, meaning it's higher up, further away from the dome, further away from the critical point, than this gas that's coming in at state 9. So this is another way of utilizing the resources that are already available within our cycle or within our system to reduce our overall inputs. So we're combining some of this partially condensed gas with gas that's far from being condensed.
Is that what like air products would do to take nitrogen from the air and get liquid nitrogen, or is that totally different process?
I don't know specifically from gas to gas how the process goes, but probably it's something similar. Liquid nitrogen, I think they can just compress it to very high pressures and it turns into liquid. It depends on how high the critical point is, really. But I know general how it works. I don't know what those thoughts are. But I don't know specifically from gas to gas if they use that cycle or not. Okay, so now we're talking about gas refrigeration cycles. So part of the reason that we want to be able to utilize these gases in our cycle, or why we sometimes need to liquefy gases, is to use them in these gas refrigeration cycles. So it's similar to a gas power cycle, like the Brayton cycle, but instead of desiring a network output, we now have a network input, which allows us to transfer heat from a colder space to a warmer space. Okay, so just like the vapor compression cycle is being run in reverse, this is the same idea, or it's the correlating cycle or mechanism for gas cycles instead of vapor cycles. And in this case, with a gas refrigeration cycle, we have 4 steps, 4 components. So we have 2 heat exchangers, a compressor, and a turbine. So this gas comes in at state 1, is compressed to a higher pressure. Consequently, it increases in temperature, so the heat needs to be removed from it. Then it runs through this turbine, which decreases the pressure further, creates some network output, but it's not enough to power the compressor probably. And then we run back through this heat exchanger, where this cooler gas can pick up heat from the environment to remove it in order to accomplish our refrigeration. Some important things to note on this reverse Brayton cycle, that the ideal cycle, we assume that at state 1, our temperature is going to be T sub L, and at state 3, our temperature is going to be T sub H. So ideally, we're able to exchange heat with the environment such that our gas becomes in thermal equilibrium with the cold space or with the warm space. So as we finish this heat exchange process here, where we're adding heat to the gas, it heats up from some temperature that's less than T sub L up to T sub L. And this temperature, which when we remove the heat, we have a temperature that's greater than T sub H that is moved to T sub H at state 3. So that's again the ideal gas refrigeration cycle where we have that happen. So if we look at this cycle, we can see that our temperature is a maximum and a minimum here. So it's at a maximum when it comes out of the compressor at state 2, and it's at a minimum before it goes into this final heat exchanger or after it comes out of the turbine. And then again, T sub L happens at state 1 and T sub H happens at state 3. So the equations for the coefficient of performance, of course, it's still this QL over work net in. We're assuming it's operating as a refrigerator, not a heat pump. If it were operating as a heat pump, it would be Q sub H over work net in. And then we can just determine in terms of property values or enthalpies what those would be. And in many cases, when we're working with a gas refrigeration cycle, it will be like an ideal gas. And so sometimes we can just replace these with C sub P times T1 minus T4, but not always. Particularly if we're operating over really wide temperature ranges, and if we're coming close to the critical point, then it's far less accurate to make that assumption that specific heat is constant. Okay, so let's do an example with a gas refrigeration cycle. And this is an ideal cycle using air as the working fluid, and it's maintaining a refrigerated space at 0 degrees Fahrenheit. So 0 degrees Fahrenheit, while rejecting heat to the surroundings at 80 degrees Fahrenheit. The pressure ratio of the compressor is 4. Determine the max and min temperatures in the cycle. The coefficient of performance, and the rate of refrigeration for a mass flow rate of 0.1 pound mass per second. Okay, we must assume variable specific heats. So when we're using an ideal gas and we're assuming variable specific heats, what tool do we need to use?
Tables.
The tables, right? So variable specific heat means you have to look things up in the table. So we'll go through again how to do that if you forgot. Okay, but let's go back to our cycle diagram and let's try to figure out what these pressures, temperatures, information is at any of these points along the way. So the refrigerated space is at 0 degrees Fahrenheit and the surroundings are 80 Fahrenheit, but they haven't told us specifically any of the temperatures within our system. Do we know any of those temperatures at this point? It's an ideal gas refrigeration cycle.
You know, 1 and 3, right?
Okay, how do we know 1 and 3?
Because of the cold part is 0 degrees, and the hot one is 80.
Okay, so at state 1, we're going to assume that when our fluid goes through the heat exchanger, it comes into thermal equilibrium with the environment. So state 1 is equal to T sub L, which is 0 degrees Fahrenheit. And while we're at it, let's just go ahead and convert that to Rankine, not Kelvin. And then state 3 is T sub H, which is 80 degrees Fahrenheit, which if we convert that to Rankine is 540 degrees Rankine, not degrees, it's 540 Rankine. Okay, so we know 2 temperatures. How do we find the other 2?
Is there the ratios or anything?
Okay, so we're given a pressure ratio is 4.
Using the reduced pressure.
Yeah, using the reduced pressure. So if we go to the table, T1 is equal to 460 Rankine. So T1 equals 460 Rankine. We go to the table and we look up PR1. Okay, so it's table A17, I think. Table for air, 17 or 18. Oh, E. 17 or 18 E. 17E. Page 972. Okay, so we look up at 460 Rankine. What's our P sub R?
127.2.
Are you in the English tables?
I think 460
At 460 Rankine,
was PR.
PR.
127.2.
Oh, you're reading too far over.
Oh, 0.7913.
Yeah.
It's going all the way across.
0.7913. Yeah, you were reading off of 1858 Rankine. Okay. P sub R is 0.7913. We know for an ideal gas that T1 over T2 is going to be equal to PR1 over PR2. That's P. So we can solve for PR2 is equal to PR1 multiplied by, no, what am I doing? Not T's. Get out of here. Start over. P1 over P2 is equal to PR1 over PR2. So PR2 is equal to P2 over P1 times PR1. What's P2 over P1?
1 over 4.
Is it 1 over 4 or 4?
4.
4, okay? So if you aren't sure, you can think, okay, compressor, what does a compressor do? It increases the pressure, so the pressure at state 2 should be higher than the pressure at state 1, which would mean that our pressure ratio, P2 over P1, should be greater than 1. is 4 times PR1, 0.7913. So we find our PR2 is equal to 3.165. From that, we can look up H2, which is 163.5, and our T2, which is 683 Rankine. T2 represents the maximum temperature in the cycle. Okay, so we found the maximum temperature. To find the minimum temperature, we go through a similar analysis where we have P3 over P4 is equal to PR3 over PR4. We can look up PR3, this P3 over P4 ratio we know. So we find PR4 is equal to PR3 times P 4 over 3. Is this going to be 4 or 1 over 4?
1 over
1 over 4, right? Because for the turbine, the higher pressure is at the inlet than the outlet. So it's 1 over 4 multiplied by PR3. And we looked up PR3 was 1.3860. So we find PR4 is equal to 0.3465. We find that our H4 is 86.7 BTUs per pound mass. That's the same units over here. And our T4, which represents our minimum temperature in the cycle, is 363 Rankine. Okay, so we found part A. Part B, the coefficient of performance is going to be equal to Q sub L over the work of the compressor minus the work of the turbine. So Q sub L occurs here between state 4 and 1. It's going to be H1 minus H4. The work of the compressor is between states 1 and 2. It's going to be H2 minus H1. And the work of the turbine is between states 3 and 4. It's going to be H3 minus H4. So if we plug in the numbers for that, for all these enthalpies that we looked up, at state 1, we also looked up the enthalpy at state 1 was 109.9 BTUs per pound mass. And the enthalpy at state 3, we looked that up, was 129.06 BTUs per pound mass. Okay, so we calculate our coefficient of performance is 2.06. That's part B. So part C, we want to know Q dot L, which is just equal to M dot times Q sub L, which is M dot times H1 minus H4. M dot in this case is 0.1 pound mass per second. H1 is given, H4 we determined, so we can calculate Q dot L is 2.32 BTUs per second. That's the cooling rate. Okay, so again, it's all the same kind of thing that we're doing here, right? We have to find property values, so knowing how to find property values is like the fundamentally most important part of solving any of these problems. So whether you're dealing with an ideal gas with constant specific heats or variable specific heats, you need to know the difference between the two and how to do that. If you're dealing with the steam tables, figuring out if it's superheated or saturated or somewhere in between, knowing how to do that is 99% of solving these problems. Then you just start plugging in numbers to Q and H, or Q and work and those equations. Okay, so there's I think two other things to talk about. One is absorption refrigeration, which we're not doing any problems on these, but it's just kind of interesting to see how this works. Now this is the way that they used to create ice, like back in the 18th century. Before they had vapor compression cycles in refrigerators, they used to use a chemical process with ammonia to create ice. So basically how this works is there is there is ammonia coming in from this evaporator. So it's vaporous ammonia that enters into this chamber that has water into it. And because of the way that water and ammonia react, when the ammonia is a vapor, it binds with the water. And it allows this ammonia heavy water to be pumped up to this regenerator. So some heat is added from other parts of the cycle so that we're trying to increase the heat or vaporize this ammonia. And then in this part of the cycle, a lot of times with absorption refrigeration systems, they just use ambient heat, like from geothermal activity or maybe from another process or from solar energy. And in this case, it's not a solar panel creating electricity, it's the actual solar energy or the heat from that to further vaporize this ammonia. So then it goes through this rectifier, which removes any remaining water to send back through the system, and that hot water helps to preheat the ammonia coming up. But this pure ammonia vapor, not a vapor, it's a liquid ammonia, is sent through. Heat is removed from it using the condenser. It's condensed further to a liquid, and it comes back to this evaporator. So by allowing this chemical process to happen here, essentially what you're doing is increasing the pressure of the ammonia vapor, is what all of that does. And it's kind of complicated, but it allows you to do it without any electrical inputs, because it's all a chemical process, for the most part, that you can just use heat from the environment in order to make that happen. And that's how they used to make ice. So it's kind of interesting. Another way of cooling that's a little bit non-conventional is using thermoelectric devices. So there are certain metals that when they're heavily doped with electrons, so that they have a higher electron content than normal, and then they're paired with a metal that has a lower electron content than normal. When you apply heat to one side, then the electrons kind of shift, which creates a current. Similarly, you can add electricity to this, these two dissimilar metals, or run a current across it, and it causes heat to one side to get hotter and one side to get cooler. So thermoelectric heating and cooling is not very efficient or effective, but it is used in cases where you want a very low noise application, or if it's in a enclosed confined space. They use it a lot for electronics cooling, just because you can cool a chip very efficiently and effectively in a very precise location with a very small device. So it's kind of another interesting idea and way, and primarily it's used in like novelty kind of applications. Not primarily, I shouldn't say that, but I mean, you can get like a refrigerator you can plug into the socket of your car and have like a little refrigerator in your car that's not, you don't have to worry about it being noisy or having any CO2 buildup or anything like that. Because you could get a propane fridge and have it in your car too, but you probably don't want to do that either. So it's primarily used in small enclosed spaces where it's crucial to keep electronic components cool, or in things like this where you just want to have a little nice cold drink in your car while you're driving. So it's just interesting. And that's it for today.